Hey everyone, welcome to this presentation at DRAMSec of Drama Queen. This is work done together with Victor van der Veen from Qualcomm and me, Ben Grass from Intel. I'd like to start by asking the question, can we forget about classical side channels? Classical side channels are side channels that exploit secret dependent accesses that victim code does. This is insecure and wrong. You're not supposed to write software this way, but nevertheless, there may be situations in which we want to show mercy to this code. So as an example, we see an elliptic curve point scalar multiplication function here. We unconditionally call the duplicate point function, and then conditional on the secret value of a bit in scalar, we call the add function. And this makes it a secret dependent access. We only call the add function when the secret bit is 1. So this code is bad, insecure, and wrong, but there may be cases in which we want to use a so-called insecure implementation. Well, there may be cases where we want defense in depth. There have been cases where previously secure code, which did viewed on a per cache line basis, was secure, and then when new microarchitectural phenomena came to light, or new exploitable microarchitectural phenomena came to light, this code was no longer secure. So MemJam is an interesting example of that. So maybe we have a secure implementation, but we don't totally trust the compiler to always keep the transformation to executable code secure, or maybe we don't trust the microarchitecture to maintain this constant time property. Maybe we want defense in depth, or maybe we just want to use an insecure implementation. So can we make this so-called insecure code securely usable after all? And in this presentation, we will look at this question. We will look at this question, number one, by proposing a cache attack immunity framework. This framework will take any kind of insecure code and make it immune from cache attacks we initially claim, the strawman design claims. Then we will look at the drama side channel signal, which is a side channel signal shown in previous work called the drama paper, to be a side channel that's exploitable from DRAM. And of course, we will see that our cache attack immunity framework will permit some accesses to DRAM. So we will see if this strawman framework will be immune or not to this DRAM side channel signal, which we will show in the third part of this presentation. All right, so let us describe the strawman cache attack immunity framework, the framework that will save us from all cache attacks. We want to forget about classical side channels in the sense that we want to be able to apply a framework that will make these insecure code that are susceptible to these classical side channel attacks. We want to make the problem go away. And the strawman design that we propose is to map all of the code in this insecure code, map all of the code and all of the data that it accesses to uncacheable. So this means that it will not leave a trace in the cache. Any attacker trying to probe the cache, or be it the L1 cache or LLC, will not see any activity in that cache because this code and this data is not allowed to be cached. So we use this framework called context light, previously proposed as a Spectre mitigation, which we then now repurpose for our purposes. We use this framework to mitigate cache attacks. Then we also disable SMT, or the OS perhaps inhibits concurrent scheduling of different security domains on the same core on different hyperthreads, from which we assume that no other kind of microarchitectural attacks are possible anymore. So that we can't assess the accesses that the victim does through the L1, L2, TLB branch buffers or anything like that. So we think we are completely safe against classical side channels. This is the proposal of the strawman cache attack immunity framework. Problem solved, right? So now that this problem of classical side channels is solved. The problem of classical cache attacks is solved. We revisit the drama signal, the drama attack that was proposed in previous work, and we show the source of this side channel signal, and later evaluate whether in the new situation where our victim code is not susceptible to cache attacks, whether it might be susceptible to drama attacks. So first, let's revisit what is the exploitable drama signal. All right, so memory in DRAM is organized by banks, and within the bank, memory is organized by rows. There are rows of bits in every bank, and every bank has a row buffer, kind of a cache. And data can only be read from this row buffer. So when a memory controller wants to access a particular row in DRAM, it first has to send a activate command, which copies the data to the row buffer. And once this row buffer has been filled with data from the row, the memory controller sends a read command, and those bytes inside the particular columns that the controller requested are sent back over the bus. And at some point, the row will be copied back from the row buffer into the row called precharge, which writes the row from the row buffer back into DRAM. So as you can tell, all these operations doing the number one are relatively slow. If you had to do this every time for every row access, for every memory access, that would be incredibly slow. That's why the memory controller will do aggressive interleaving to spread out memory operations, which typically exhibit lots of locality, spread them out over as many banks as possible, so that lots of accesses that are close together in time will end up into lots of different banks, so that all these operations can be done concurrently rather than in serial. So we're hoping that the next access is in a different bank. So here is a bigger picture. Here we see a system comprising many DRAM chips, each of which have many different banks, each of which have many different rows. And as long as the accesses fall into many different banks, we can do all the previously seen operations in parallel, which is great for performance. In this case, we're seeing accesses happening to different rows in the same bank, and that'll be slower because that is what requires these operations we previously saw to be done in serial. So here we see the reason that these things are slow. So in the case where we access the same bank in different rows, we have to activate a row in bank P, issue the read command, and then pre-charge bank P. If we want to then access row Y, the second address in the same bank, we again have to activate row Y in bank P, issue a read command, and then pre-charge bank P again. Whereas in the case where we have different banks, we can do all this parallel and get a fraction of latency. So this is a bigger picture showing what this kind of latency looks like in practice. So this experiment shows a heat map of latencies where we access two different addresses. We measure the X latencies of two different addresses together. And on the x-axis is address number 1, on the y-axis is address number 2. And the color at each point shows the latency of the access of both addresses together. So if these two addresses fall in different banks, then we get the green color, which is most of the chart, and we can do these accesses in parallel. Of course, there's some contention in other areas of the system, like same channel or not. But the biggest effect, as you can see, is the so-called bank conflict. If we have two addresses that fall in the same bank, then we get this higher yellowish color, showing that operations have to be serialized when falling into the same bank. The darker shade on the diagonal is when we have the same row in the same bank. And that means that there's no switching, no activating or pre-charge necessary at all for accessing these two addresses in a loop. because we can just access the row buffer over and over and over again, and it acts as a cache. So then, well, that's actually the optimal case. All right, so now having shown the source of the signal of drama and our strawman cache attack immunity framework, let's apply this framework to this victim code and see if the drama signal is usable as a side channel. So this assumes that the attacker can be co-resident with the victim in the same DRAM bank. The attacker will monitor that particular cache line, its own particular cache line, right? It's different memory from the victim, of course. The attacker will monitor the latency using uncached accesses of its own cache line and generate a execution trace this way. This is just the latency of its own cache line. And whenever the victim is co-resident in the same bank as the attacker is, we may expect some perturbation of the latency of the attacker's cache line, because whenever the victim does accesses, we can expect the latency of the attacker to go up. And if this latency pattern is perturbed in a different way for different secrets, for different activity that the victim is exhibiting, then we may be able to mount in the case of cryptocode, a key recovery attack. So let's see if we can do that. So the attacker monitors a single address. We apply the attack immunization framework, the cache attack immunization framework. We expect us to be perfectly immune from cache attacks, and the attacker now monitors a single cache line to monitor the DRAM bank conflict signal. So let's see if we see any secret-dependent latency patterns that the attacker sees. So this is an example of a single latency trace that the attacker sees. The background shade indicates the ground truth of what the victim is doing in that phase. The blue shade indicates the add function that is only ever invoked when the secret key bit is 1. And the green shade indicates the duplicate function, which is always invoked, whether the secret key bit is 0 or 1. So we want to try and identify whether these functions, the pattern of these functions that are happening, and then recover the execution trace at a higher level, because that corresponds directly to key bits. As you can see in the latency trace, especially after smoothing, the latency signal is very characteristic. It's very low noise, and there's a very clear distinguishable pattern that's different between the green background shade and the blue background shade. So what the attacker then does is train, using some ground truth, it trains an SVM classifier on that signal. So it says, well, when you see the start of a blue section, you'll see this kind of pattern. The start of a green section is this kind of pattern. And then please tell me, when given an execution trace without ground truth, what are the patterns that you see? And the classifier output is on a test trace is seen in red together with the ground truth. And in this particular case, it's a perfect result. It's not always perfect, but in this case it is. And when it's not perfect, we need some brute force to get at the real key. And a histogram of many test cases showing the amount of estimated brute force necessary to get from the guess at that time to the real key is shown on the right. And as we can see, in the majority of cases, less than 1 million brute force tests are needed. So we conclude that this is a very practical attack. So to conclude, this side channel immunity framework will probably work against cache attacks, against concurrent cache attacks, but if it wants to be a complete defense, it should consider more shared resources. And we show in this study the example that DRAM is a shared resource that should not be ignored. So currently it's not a complete defense. There may be software defenses that help flesh out the defense. The OS may be able to provide DRAM bank isolation, which would help, of course. And that concludes our presentation. Thanks for your attention.